persons who have actually come forward. Even today's resource person, Professor Tulasi Ramdas Garu, was actually kind enough to continue to do the third spell here. Thank you so much, sir, on behalf of all of us. Necessity is the mother of invention. Whenever you need, and human race has always tried to invent new things. For the past 100 years, the human race have been plundering the fossil fuels and whatever energy resources that we had. We were depending on normal, conventional electricity and other resources in the form of coal, water, whatever it is. And even when it comes to fuels, petrol and diesel were being drawn from the earth, which have been accumulated for some centuries. In this 1 century itself, we have now drained out everything. And I think in the next few generations will not have all these things. As we have seen now, India has never been online in learning or this one. Only we could see our engineering college students or faculty members, they were always enjoying the offline this one. The best of the trainers in the world used to come online, but our people have never gone onto it. Now see the situation. We are only online. We are never into offline because of this COVID. Now, if you require, I think that emergencies will make us learn how to make new things. Same is the situation with our, resources also, energy resources. We have been doing all conventional. Now we are renewable energy. We have never taken it very seriously because of the time, because of the money involved, and whatever may be the reason. Now the whole world is looking into that. Now when the regular resources are over, people are all looking at these resources. Now we look at European countries, China, especially in Asia, have been forefront in taking up renewable energy resources. And now India is also picking up, but of course, you can look at statistics. When you look at China and India, there's a huge difference. When China and other countries, there's a huge difference. I think there was a question, can the world convert the whole, the world convert the renewable resource 100% very soon? Yeah, by 2050, most of the countries can do it. And if the politicians and the rulers think about it, definitely it's possible. Nothing is impossible. Of course, they need the dedication. Initial investments will be higher, but definitely that will definitely help the human race a lot. Now, there are some countries which have already banned petrol and diesel vehicles by 2025. Most of the European countries have done it. There are some countries which are already almost 100% into renewable resources. So countries like India and other countries can definitely do it. And if the technologies that are coming up and new innovations come up into that, and if it's going to be a little cost effective, definitely things will be there. The biggest challenge is distribution and storing. And in this session, you're going to listen to Dr. Professor Tulasi Ramdas Garu and various other resource persons, how all these challenges can be met. I would like to once again congratulate all of you and request all of you to sincerely take part in this training, because AICTE is sponsoring this. They are giving you the funds. Your colleges are giving you the OD to attend these conferences. Please keep all the works aside and focus on these trainings. You just don't do it for namesake, for certificate sake. For knowledge, if you can do it, definitely you can do it. And I request the convener here to please make sure that every attendee should speak for at least 2 to 3 minutes in the valedictory session this time. I request Jay Krishna to please make sure that every attendee, every participant should at least speak for 2-3 minutes and extend the valedictory session if necessary, or shorten the other sessions. Make the speaker speak, learners speak what they have learned, not just filling the feedback. That will definitely help you to see how good your training sessions were there. Once again, thanking all the resource persons and the conveners. All the very best for this last training program of the AICTE sponsored STTP program. Thank you.
Thank you, sir. Thank you for your valuable words. Now I would like to introduce our today's guest of honor and session speaker, Sri Dr. G. Tulasi Ramdas sir. Dr. G. Tulasi Ramdas sir, former Vice Chancellor of JNT Kakinada. Sir has done PhD in simulation and analysis of PSSM drives from IIT Madras in the year 1996. Sir stood many positions in our JNT Hyderabad and as well as in Kakinada. I'll just list out all the things. HOD from 2000 to 2002, Vice Principal 2002 to 2004, Principal 2004 to 2006, Director Academics and Planning 2008 to 2010, Registrar from 2010 to 2011. After that, Sir went as Vice Chancellor of JNTU Kakinada and worked as 2011 from 2011 to 2014. Sir has a vast teaching experience and published many national and international journals. Sir guided many PhD and MTech students. Sir acting as a reviewer for a good number of journals in electrical engineering. And Sir areas of power electronics, electrical motors and drives, fax system, power quality and renewable energy sources. Now I request Sir to take up the session on energy scenario in India, different categories of renewable energy sources.
Thank you, Krishna.
Thank you, sir.
So, good morning to all of you.
Good morning, sir.
At the outset, are you able to hear, Krishna?
Yes, sir.
So, at the outset, I congratulate the St. Peter's Engineering College in general, and in particular, Department of Electrical Engineering for conducting this wonderful workshop or STTP sponsored by AICTE in a third spell on the topic recent trends in renewable energy sources and their integration to smart grid. I also thank the Secretary Sri T.V. Reddy Garu, the Principal Dr. Srilata Madam, and the convener of the program, Dr. Brahmaya, and the co-convener, Dr. J. Krishna, for conducting this program. And dear electrical engineering fraternity of teachers from all institutions across the country, and the faculty members of this department at St. Peter's Engineering College. Again, very good morning to all of you. And let me take the introduction of the renewable energy in India. It is like an overview of the renewable energy. The contents are divided into this form. Initially, with some introduction about the renewable energy, their importance, then the global and Indian scenario, few statistics so that we can understand the importance and the progress and the focus in the future about the renewable energy. Then projections of renewable energy generation in India, then solar PV power systems, then wind power systems, then grid connected hybrid renewable energy, grid connected offshore wind energy through HVDC link to the onshore distribution, then research avenues in solar and wind energy areas. So this is how I planned this lecture about 2 hours from now. I'm suffering from severe cold, so you have to bear with me in between, okay?
Yes, sir.
Okay. So the introduction goes like this. In the near future, the demand for electrical engineering is expected to increase rapidly due to the global population growth and industrialization, and because of the depletion of the fossil fuels also. A very good introduction was given by both T.V. Reddy Garu and Srilata Madam Garu on this subject. So world's net electricity generation is expected to rise from 22.5 trillion kilowatt hour in 2012 to 26.6 trillion kilowatt hour in 2020, and 36.2 trillion kilowatt hour is expected to be completed by 2035. So that is the world's electricity generation projections. To overcome this kind of demand and targets and the problems associated with conventional generation of electricity, mostly from fossil fuels, renewable energy sources can be participated in the energy mix to supplement the electrical power demand. The energy and environment is of very prime importance because of the global warming situation due to climatical change. That is a major problem addressed by many countries in a common forum, and they have also taken a lot of initiation to promote the environment friendly energy generation across the globe, and also to have the sustainable development of the same energy source. So the industries, the vehicular traffics on the roads, and other forms of energy development creates or generates a lot of carbon dioxide, which is increasing the temperature of the Earth, planet Earth, and with that the temperatures are risen from 2 to 3 degrees, and ultimately it may reach to 50 degrees or beyond. Then the sustainability of life or biodiversity life will be a big threat. What are the effects of ill effects of conventional energy? The world relies mostly on fossil fuels from centuries, and around 70% of the energy is generated all over the world from fossil fuels like thermal, hydel, and gas. Other than energy production, industries also emit carbon dioxide and other greenhouse gas emissions. Then humans or their part pollute atmosphere by day-to-day activities by using diesel vehicles or petrol vehicles, which are available, of course, and also other unhygienic, practices, civic practices. Why renewable energy? The demand for energy in the country has been growing rapidly, and our fossil fuel resources are depleting, or and another side, global warming is also taking place. These are the reasons for the choosing for or going for the renewable energy. The current trends indicate clearly that the country would be facing constraints in indigenous availability of conventional energy resources, such as petroleum, gas, or the coal, okay, for thermal generation, and water resources like reservoirs, and the rains are also not occurring timely. All these are the conventional resources for energy production. The inability of the conventional systems to meet growing demands in equitable and sustainable manner. So everybody depends on electricity now. Every gadget has the requirement of electrical energy. No need to efficiently and economically meet the energy needs of all the citizens across the globe, and particularly in India, in the rural also. rural villages also. Need for renewable energy continues, like the advantages are it will offer the clean environment without any pollution, zero emissions, and we can have unlimited supply since it doesn't depend on fossil fuel, and the resources are perennial, is a permanent one. As long as sun shines in our country, we can always have the solar energy. As long as wind flows, we will have the wind energy. Then zero greenhouse gas emissions, decentralization of power generation and also distribution. That is unlike conventional power generation, where the coal mines, the thermal power station should be nearer to the coal mines. Similarly, the hydel power station need to be location restricted where the reservoir or source of water is available. But we have to transmit to the all corners of the country. But whereas the renewable energy, wherever wind is there or solar, anywhere is available, so there is no restriction. So we can always have decentralization, and we can generate there and there itself and distribute with, among themselves or their villages. And we need not have to transport from one corner to the other, since everywhere the solar energy is available. But wind energy to some extent is a location based. Enables rural and island electrification. It is also explanation of decentralization.
5 minutes, sir.
Pardon?
Yes, sir. Yes, sir. Yes, sir.
Creating employment opportunities in this area, starting from R&D, manufacturing, distribution, power generation, maintenance, commissioning and maintenance. Then social development also possible with this, so that every nook and corner will get, we can offer the power supply at a cheaper price. Renewable energies are divided into several categories, like wind energy, the solar, and then geothermal, okay, and then the wave, okay. Wave is depends on kinetic energy, and the tidal wave with the tides of the in the ocean will get different tides within the water, under the water. The waves are on the surface of the sea water. That is the difference of tidal and wave. Both are connected to the ocean. Then OTES is the ocean thermal energy conversion. Okay, these are the varieties. So last three are sea dependent. The remaining three are on different resources like wind and solar and water. Even hydro projects are also slowly joining the renewable energy resources. Then global scenario, like solar PV generation capacity and wind energy capacity, both are given separately, and you can see the color code from bottom. Here you have to see from top to bottom on the name side, and the figure spectrum from bottom to top. So let us see Japan first, light yellow, which is at the bottom line. Okay, so this is Japan, and then next is Germany, then green one is the US, then Italy is dark yellow, and then China is blue, and rest of the world is again yellow. So you can see you can compare this end at 2017. Okay, their production is highest. So the China is generating large solar power capacity, than the rest of the world. Okay, so that's how the progress is. And the next best is the Japan, and most of them are south in the Asian countries. Okay, which are involved in high power generation. And you can see the wind energy capacity again from the bottom. US is at the bottom level, then Germany is the next highest, and then Spain entered into that in a smaller capacity. Then again blue is the China, the highest in the wind also, and Spain, India is a light blue, okay, moderately started, but better than the Spain. Then the rest of the world is here. So China is dominating both solar and wind energy because they have started much earlier. Okay, you can see here the not much progress in US. US is higher side when it was in 2008 when compared to China. China started modestly and now dominating. In solar also you can see here China was never there before 2010 in solar power generation, but it was not dominated till 2015 or 2014, and then exponentially risen from 2015 to 17 within 2 years. Now it has been risen much higher. We don't have data of 2019. Okay, so that's how, anyway, if you can extrapolate, it is the highest in the world. Okay, so that's how the progress has taken place from last 9 years. Then global investments in renewable energy, like this solar, it is from 2005 to 2018 the data, and first quarter, second quarter, third quarter, and fourth quarter, right? 1 year is divided into 4 quarters, and the investment for yellow one is solar, wind is the blue, and violet is others, and biofuel is green. So you can see the here how the investments have took place. So left side is $1 billion. Okay, so $100 billion is the scale, highest scale, but maximum $90 billion were spent in 2015, right? So they are all mixed mode. Okay, so this is how the global sector wise investment on all kinds of renewable energies. And now let us see the Indian status. The India's installed capacity from all sources like renewable and non-renewable. India is the world's third largest producer of electrical power and third largest consumer also of electricity. Then the national electric grid in India has an installed capacity of 373 gigawatts, okay, or 3,73,436 megawatt as of 31st October 2020. So this is the latest information. And renewable power plants, which also include large hydroelectric plants, constitute about 36.17% of India's total installed capacity. If you take alone eliminating hydropower plant, then it will be very meager value. Okay, only for renewables. So hydro plant is also connected to the renewable energy. Okay, so now let us see the total installed capacity on as of 31st October to 2020 by different sectors like central government, central sector, the state government sectors, then private sector. If you can see in the megawatt, it is 93,927 megawatt is contributed by central sector, which was 25.2%. Then the state sectors, all states together, 1,03,617 megawatt, which amounts to 27.8. So state sector is contributing a little bit more higher than the central sector. Now private sector is highest, 47%. Okay, total 3.73436, which matches with the October figures of the country. Now next slide gives the distribution among the different sources. The blue one is a which is contributing 63% of the total power generation is through this source. The renewable energy is the pink one, which is 23%, and hydropower is 12%. If you join hydro also here, 23 plus 12 is 35%. Okay, then 2% is on a nuclear side. So this is our Indian distribution of power generating sources as of 31st December 2019. Then the different ministries are developed to monitor, they encourage, invest on the renewable energy, which we have started in 1982. A small department of non-conventional energy sources have been established by the government of India to look after the initiation and progress of the new and renewable energies. Then in 1992, the same department after 10 years upgraded to Ministry of Non-Conventional Energy Sources, which are called MNES. Then later again in 2006, after 6 years, the same center is renamed as Ministry of New and Renewable Energy. So earlier we used to have called non-conventional. Now we call New and Renewable Energy, MNRE. Still this name is valid now. To support the ministry, which ministry? Ministry of New and Renewable Energy. There are 5 institutions consisting of 3 academic bodies. Later on, different times, they have created different centers, like department. If the MNRE is a college, then we have like departments. So we add each one depending upon importance. So those 5 are like this. The National Institute of Solar Energy, which is called NISC, which is established in Haryana, and National Institute of Wind Energy, NIWE, which is located in Chennai, Tamil Nadu, near sea coast. The National Institute of Bioenergy, NIBE, located in Punjab. So these are 3 institutions are developed for looking after the R&D activities, then suggestions, then fund allocations, the progress monitoring and all that. So to public sector undertakings like Indian Renewable Energy Development Agency, EREDA, popularly known as EREDA, and Solar Energy Corporation of India, both are located in New Delhi. Okay, these are the 5 institutions which are supporting the activities of the Ministry of Renewable and New and Renewable Energy. Now, under Ministry of New and Renewable Energy, we have grid interactive installed power capacity from last 5 years given in megawatts. So different sources, and as on 31 March 2014 and as on 31 March 2019. This is the 5-year data. The wind power was 21,042 megawatt. Now it has reached to 35,625. So in 5 years. Then solar, it was 2,631. Now it is 28,180. So exponential progress took place. And small hydel power, SHP, 3,800 is risen to 4,590. Then biopower 8,040 to 9,900. So we all put together renewable energy. It was 35,519 megawatt in 2014. Now it has risen to 78,300. So good improvement or progress in last 5 years. So you can see the grid connected renewable power, wind power in April, December achieved 1878, but up to again within 6 months it has took place almost double the capacity. So solar power, they are ground mounted and rooftop. Okay, ground mounted and solar parks, and rooftop is on the official buildings or domestic buildings, residential and colleges and so on and so forth. There 536 risen to 2,333. So within 6 months. And 5,000 solar power ground is 31, 6 times. So small hydel power which was 78, now 4,671 up to December cumulative. Then waste to power. Okay, so that's how the total power which was achieved by that time is 7,500 and achieved here is 85,900. So enormous progress have been took place. Now renewable energy at a glance in India, which is grid connected, like wind power 35,000, then solar ground power, then solar rooftop, then small hydel biomass due to bagasse generation, then biomass non-bagasse is very small, okay, and then waste to power or waste to energy just started, which is total amounting to 78,316, which was given in the last table, okay. And the off-grid captive power, waste to energy and biomass and solar power. Solar power is dominating in this. These are the figures as of 31st March 2019. Then comes to the grid interactive capacities, like the first one is an off-grid between 1 year. So what is the progress between 2017 to 2018? 17 is red one, then blue one is 18. So this is the increment took place in solar power, but increments did not have taken place in the other two sources. And this is also grid connected. First top one is off grid and the bottom one is grid connected. So here the solar ground mounted, there is a lot of improvement took place last 1 year. And sector wise renewable energy, as of December 2019, wind power contributing 37,000 megawatt, solar power 33,000, small hydel 4,600, then bio is 9,900, better than this small hydel power. Then waste to energy is just started. Okay. Then solar installations in top 10 states as of December 2019. Karnataka is the toppest in solar installation, 7,200 megawatt. Rajasthan 4,800, Tamil Nadu 3,700, Telangana 3,600, Andhra Pradesh 3,500, very close to each other. Gujarat 2,700, Madhya Pradesh 2,003, Maharashtra, Uttar Pradesh, Punjab, and so on and so forth. These are the top contributors. Now, year-wise cumulative capacity of renewable energy, last 10 years by all means. So, which was started in 2008-9 to 2018-19, and there is a gradual progress and reached to 78,360. Then the bottom one is the yellow lines are only the solar power installation from last 10 years. So here almost 0, 0, 0, and then small increment here, then progress. So there is an exponential incremental from last 5 years, or 1, 2, 3, 4 years, 4 to 5 years. Okay, reach to 28,000. Okay, so that is the progress we can see in bar charts. And what is the projection now? We have seen the history. Now what are the projections? India has a large renewable energy potential from different sources like wind, solar, biomass, small hydel projects, etc., waste to energy, etc. As per estimates, India has a wind potential of more than 300 gigawatt at a hub height of 100 meters, and solar potential of 750 gigawatt. So put together 1000 gigawatt. Assuming that 3% of the wasteland is made available for the solar parks, which needs larger space. Small hydel potential is about 20 gigawatts and bioenergy potential is 25 gigawatts. So almost like 1,100 gigawatt capacity we have. We don't know how many years it takes to reach them. The India's INDC means Intended Nationally Determined Contributions, that builds on its goal of installing 175 gigawatt of renewable power capacity by 2020. So our target is to reach 2 to 175 by renewable energy by 2022. Okay, still we are in hundreds only, but we have potential of thousands gigawatts. By setting a new target to increase the country's share of non-fossil based installation capacity to 40% by 2030. So from 22 to 2030, all put together will have 40. Now how much is that? We have 12% idle plus 23. How much is that? 45. So if you remove the idle here, small idle or whatever, so we have only 23. So that 23% will be increased to 40% by 2030. So almost 10 years it takes to increase 16%. So solar PV, now this is all put together. Now we'll see how much solar power can contribute. As on 31st December 2019, a total solar power capacity installed was 33,730 megawatt or 33.7 gigawatt. The target of the solar park scheme is to develop at least 50 solar parks with an aggregate installed capacity of 40,000 megawatt by solar power by 21-22, another 1 year. Next, the wind power, the government through National Institute of Wind Energy has installed already over 800 wind monitoring stations all over the country and issued wind potential maps at 50 meters height of the blade or wind hub and hub height 80 meters, 100 meters, maximum is 120 meters above the ground level. That is a tower height. Okay. Then the latest assessment indicates gross wind potential of 302.25 gigawatt in the country with 100 meters hub height and 695.5 gigawatt with 120 meters height. So 120 meter height has got lot of potential, double the potential of what we have had 100 meters. Put together it is more than 1000 gigawatt. These are all above ground level. The country currently has the 4th highest wind installation capacity in the world with total installed capacity of 37.5 gigawatt right now. Okay. So this was on December 2019. Then among the wind, we have offshore because we have 3/4 of our country is located with the sea. So we have a lot of potential on the offshore. So offshore is situated in the sea. Onshore means on the ground, but border of the sea. Owing to the vast potential in the entire coastline of both, coastline is on both the sides, west and east. Then offshore wind energy in India can provide the desired results to realize the climate commitment and energy security the country is thriving for. Initial assessment of offshore wind energy potential within the identified zones has been estimated to 70 gigawatt of the coast of Gujarat and Tamil Nadu. They have only identified these two zones, okay, to start with. Okay, they only to contribute 70 gigawatt. In the area of 365 square kilometers for 1 gigawatt offshore project in Gulf of Khambat of Gujarat coast has been completed. So they have taken covered 365 square kilometers to locate the offshore turbines and towers for producing 1 gigawatt. Offshore wind energy development is a very capital intensive. Normally it is a capital intensive even in the onshore. If it is offshore, it is very difficult to construct the towers, foundation and all that. And the initial investment is very high, but running cost will be maybe comparatively low. In order to attract the large investment for development of the sector in India, Government of India has already announced its intentions of developing 5 gigawatt of offshore wind energy project by 2022, another 2 years time, and 30 gigawatt by 2030 by inviting private parties. And wind solar combination, PV hybrid system, they are called hybrid system. Wind and solar is through PV, photovoltaic cell. The ministry issued a national wind solar energy policy on 14th May 2018. How to combine them and what is the policy, who will go and near to what. If you have wind potential, solar will go and join with the wind. If the solar PV is very high and there is a possibility of wind, we can construct wind near the solar PV. Okay, both ways. The main objective of the policy is to provide a framework for a promotion of large grid connected wind solar PV hybrid system for optimal and efficient utilization of wind as well as solar resources, both the transmission infrastructure and the land acquirement. So the wind solar PV hybrid system will help in reducing the variability in renewable energy power generation and achieving better grid stability. So because wind and solar PV, they are dependent on their respective resources. Like wind is not always the same direction or same velocity. So wind will change, but the power also changes accordingly. So if you want to connect to the grid, the power need to be constant, the voltages and frequencies need to be constant at the grid, but which is variable. Now similarly solar PV, during the different times sunshine varies. In cloudy days they are different, and nights we don't have sunshine. So all these, they are time dependent, so their output is also not constant. So because of that, if we can combine, one can supplement the other can supplement the other, so that at the end product we can have the better grid stability and maintain a constant voltage and constant frequency to some extent, better than standalone situations. The policy also aims to encourage new technologies, methods, layouts involving combined operation of wind and solar PV systems. Then biomass. The ministry has been promoting biomass and bagasse cogeneration program with the aim to recover energy from biomass, including bagasse, agricultural residues such as shells, husks, de-oiled cakes, and wood from dedicated energy plantations for power generation. So all these industrial residues, we can create the biomass power. The potential of power generation from agricultural and agro industry residues is estimated to about 18,000 megawatt. Power generation through bagasse, cogeneration in sugar mills, sugar cane wastage is about 8,000 megawatt, and the total estimated potential of biomass power from all resources 26,000 megawatt. It can be from industrial waste and agriculture waste, okay, or the sugar mill waste. Over 500 biomass power and cogeneration projects with aggregate capacity of 9,000 megawatt have been installed in the country up to December 2019. But still we have potential of triple times, 3 times potential. Waste to energy, the program on energy from urban, industrial, agriculture waste aimed at generation of biogas, bio-CNG, and power from different wastes such as vegetables from hotels, hostels every day, from markets and other market wastes, slaughterhouse waste, agriculture residues, and industrial wastes and effluents continued during the 2019-20. So nothing can be wasted. It can be energy, generated energy, not only electricity, but some gas and other resources, okay, the other byproducts. About 100 tons per day of cow dung can generate roughly about 16,000 kgs of bio-CNG gas per day for cooking purpose or for any other burning purposes. In addition to bio CNG biogas plants generate organic fertilizer as a byproduct which is valuable for agricultural fields. Such projects are being set up in a number of industry sectors, namely distillery, paper and pulp solvent extraction, dairy, starch industries, sugar mills, pharmaceutical industries, etc. And sewage treatment plants also can have some meaningful resources. Then 139 megawatt capacity grid interactive power projects, 114.9, 115 megawatt capacity off-grid power projects have been set up by December 2019. Then small hydel power, the Ministry of New and Renewable is vested with the responsibility of developing hydropower projects of capacity of to 25 megawatts under a small hydropower project scheme. So we have the micro hydel if the power capacity is 0.1 megawatt, mini hydel if it is between 0.1 megawatt and 2 megawatt, and small hydel between 2 megawatt and less than 25 megawatts. If it is beyond 25 megawatts, it will go to the high hydel power, normal hydel powers. Then the estimated potential of small, mini, micro together hydel projects in the country is 21,000 megawatts from 7,100 sites located in different states of India, mostly in the hilly areas where the waterfalls will be their natural waterfalls, and making use of that waterfalls we'll have the small tanks, and then from the tank we can run the penstocks or pipeline so that we can create power from the hydel. The national target of SHP is to achieve a cumulative capacity of 5,000 megawatts by 2022. So an aggregate capacity of 4,600 megawatt have been already achieved by 31st December 2019 through 1125 small hydel projects. Now let us see the in-depth what is the solar energy, how it can be converted, and why solar. Because they are abundantly available in our country, almost 300 days of a year. The negligible carbon dioxide footprint, no moving parts, there are no noise of production, no water consumption, no emissions, less geographical restrictions. These are the advantages of PV solar cell. Then how the photovoltaic cell has developed. The history goes like this. The first practical photovoltaic was invented at Bell Laboratories in 1954 by Daryl Chapin, Kelvin Fuller and Pearson. The three people, you can see them here. The use of photovoltaic system for electrical power generation started in 1970 and is currently growing rapidly across the world. Till that time it was used for some other applications, but not for power generation. Now, the definitions for photoelectric, how the name have come to photovoltaic, PV. The ejection of electrons from a substance by incident electromagnetic radiation, especially by visible light, and then first observed in 1838 and explained by Albert Einstein, for which he got Nobel Prize. Then photovoltaic or PV system convert light energy into electricity. The term photo is a stem from the Greek word phos, which means light. Volt is named after the Alessandro Volta, a pioneer in the study of electricity. So photo and voltaic is then could be literally mean light electricity. So electricity generated through light. So photovoltaics is a field of technology that uses solar cells to convert sunlight directly into electricity. That's how the solar PV name has come. How solar PVs work? PV cells are made special materials called semiconductors, and in this case silicon. When a photon, a light particle, hits the panel, it has enough energy to knock an electron loose, allow it to freely flow. That's how the current will flow. The panel then has several electrical fields to force the electrons to move in a certain direction, creating a current which can be used to do work. Then you can see the typical solar cell, which has A, B, C, D, E, F layers. So 6 layers. So A is a top cover, is a cover glass. Then B is an anti-reflective coating. C, contact grid. D is N-type silicon. E is a P-type silicon. These are the 2 semiconductor device. Then black contact. So sunlight falls on the glass and then passes through different layers to generate the power. Now you can see the panel on the rooftop. This sunshine hits the panel. Panel will generate the current, DC current, charge controller. Then DC loads are directly connected to the charge controller, and through charge controller it charges batteries. The charge controller is important here, which will not allow the battery for overcharging and also for undercharging. So battery supplies to the inverter. Inverter converts the DC to AC and supply power to the AC loads. Okay, so this is how the rooftop solar system works. The concept of solar PV technology, here we can see the N layer, P layer and junction, and the enlarged photo also you can see. So that's how the power gets converted and current flows through this. And each one is a cell, each cell. So there is a combination of cells in series parallel to form a panel. Now this is the PV module behavior to temperature. So cell temperature is taken as 45 degrees centigrade, and incident irradiation. So the sunshine reaching to the glass or the semiconductor is 1000 watts per square meter area, or 800 watts per square meter area, 600 watts, 400 watts, 200, depending upon the different intensities at different times. Then how much power it generates? The operating point. This is the operating point. 229 watts, 180 watts, 132, 85 and 40. So more is the irradiation, more power will be generated at a particular temperature. Then this is at a different temperature, cell temperatures. So here cell temperature 10 degrees, 25 degrees, 40 degrees, 55 degrees, 70 degrees. So cell temperature on summer in Rajasthan area 70 degrees. Then cell temperature at Shimla or Kashmir 10 degrees centigrade. Then their powers are different. Okay, so the cell temperature is highest, the power is low. Temperature is lowest, power is high. So it will have the heat losses in the cell. So that's how this picture conveys that information. And when you see photovoltaic technologies, we have bulk crystal and monocrystal silicon, EFG silicon, polycrystalline silicon, then silicon film. These are the 4 categories in crystal silicon. Then thin film, amorphous silicon, then cadmium telluride silicon, then copper indium diselenite, CIS or CIGS. So these are thin film technologies, and the advanced technologies are gallium arsenide and indium arsenide, and concentrators. Concentration, the combination of all these things. Okay, permutation and combination of those concentrators. These are the different technologies being used. Now, crystalline silicon solar panel. Most of the common solar cells are used here because of these advantages, like high efficiency rate 15 to 25%, high stability, high reliability, ease of fabrication and longer life. The major types of silicon PV cells, like thin film 12 to 18% is efficiency, polycrystalline 16 to 20%, monocrystalline 16 to 20, and hybrid 17 to 23. All combinations are called hybrid. Okay. Now, as of now, polycrystal or monocrystal is having highest temperatures, highest efficiency. Then photovoltaic array nomenclature, this is a cell, and if you have too many cells connected in series parallel, then it becomes module. If you have different modules connected in the panel, then it is called a panel. And if many panels connected is called an array. So this is the difference between cell, module, panel and array. The average area of PV needed to generate 1 kilowatt of capacity through solar. Monocrystalline silicon, it requires a smaller area, 7 to 9 square meters for generating 1 kilowatt. Polycrystalline 8 to 11. Thin film 11 to 13. Thin film CD cadmium type 40 to 18. Thin film amorphous silicon 16 to 20. So this thin film requires more area to create 1 kilowatt. Okay. A typical residential grid connected PV system, we have already shown you. So solar panel or arrays are connected here, and then it creates a power, and inverter generates, supplies the AC power, and these are the AC loads. And then these are bidirectional to the grid connected. The remaining power you have, whenever you are not utilizing, it can be connected to the net meter. Okay, bidirectional meter, and then distribution board, and then power sent to the utility. If you have shortage of solar power, you can draw from the utility. So this meter is net meter. And PV instrumentation, inverter, wiring, batteries, charge controller. Charge controller prevents batteries from being overcharged. Disconnecting switch or connecting switch, then electrical meter, net meter. So those are the terminology used. This is an array, charge controller, battery, inverter, AC load and DC load directly taken from the battery or charge controller. Now DC systems and AC systems, there are two varieties of systems in PV solar. In the direct system, PV is directly connected to the load, DC loads. Example like fan and pumps. Okay, this is called remote direct use. And the second system is, in between you have the charge controller and battery. So in between the PV and the DC load, charge controller and battery. Charge controller controls the battery for overcharging. It will prevent overcharging so that the battery cannot damage, and battery can supply DC supply. We also have an alternative path so that charge controller also can charge the DC load. And then the AC version, there are three categories. First category PV, then inverter converts DC to AC, then switch, disconnection and connection switch, then it is going to the AC load. So PV, inverter, AC load. And if it is a grid connected, grid is connected to the net meter is connected to AC load through a disconnection connection switch. Then second one, this is called a grid tied net meter, bidirectional power flow. The second variety AC systems, grid tied dual meter. So PV to inverter, inverter to the meter to grid. Okay, again grid to the meter to AC load. We can also have connected to the grid and draw power to the grid, so that whatever we generate is directly connected to the grid, and we will be getting the grid charges. And from there, meter, whatever we draw, we have to pay for that. Then third system is grid tied with battery backup. So PV cell to power center, then critical AC loads can be addressed. Then the PV center to meter, disconnection switch to the grid, or from the grid meter and AC load. So there are three different versions for route plan. Okay, for AC system. Then factors to be considered while selecting an inverter. We have the specifications for inverter. Auto wake up, then in input voltage range, output voltage range, and the type of waveform, efficiency, maximum power point tracking, DC bus over voltage handling capability, DC bus over current handling capability, internal temperature generation, self power consumption, output frequency, power consumption at standby, environmental protection, grid code as per Indian standards and certification. So these are the factors we need to select the inverter. Then PV inverter topologies, PV inverter with low frequency transformer. There are different configurations. So PV array, then capacitor, and then DC to AC inverter, then filter, LC filter, then low frequency transformer for isolation, and then the load, okay, load or grid. So what are the advantages of this combination, this circuit? Extremely robust, electrical separation from grid for isolation, and disadvantage is high weight and large volume because of the transformer. Low frequency transformer will be larger in size. Okay. Then compared to PV inverter with high frequency transformer. So transformer is always used for isolation. So in this circuit configuration, we have PV array, capacitor, DC to AC inverter, then the transformer, high frequency transformer, which is smaller in size, but frequency is very high. Again produces the AC to DC, AC is converted to DC again, then filter, LC filter, then DC to AC inverter, then filter again. Then so critical loads we require this kind of arrangement. So we require one high frequency transformer but two inverters. Advantage is low weight, small size, electrical separation. Disadvantages: reduced efficiency, more complexity, and increased cost. Reduced efficiency because of the two inverters and high frequency transformer. More complexity because of the too many semiconductors are in place, and increased cost also obviously the same. PV inverters without a transformer, it is called transformer less. Okay, so the connection is a PV array, then step up converter with a boost converter, and then the DC to AC. After filtering with capacitor, we have bridge circuit, inverter, then filter, again load. So advantage is reduced inverter size, reduced inverter cost, weight, improved efficiency, and the disadvantage is no electrical isolation. Okay, any problem on the load side will be reflected on the source side. So that is a problem. And the centralized technology, like you can have many parallel connected arrays into single inverter. The disadvantage here is high voltage DC cables, reduced system efficiency in a central MPPT, maximum power point tracking is required. So non-flexibility here. So if anyone is failed, the power is reduced here. So in the string inverter type, we have independent panels and independent PV inverters, separate inverters for each one of them. Load is commonly connected. Okay. So advantage is system efficiency improved at partial shared conditions. Okay. So these are the two different connections. Applications, kilowatt, this is the park. So PV solar park at Maushani Island, and transporting PV systems at a remote hilly location. So this is the transporter. Okay. Then satellite earth station at Poo, and 100 kilowatt power plant at Kilton Island, Lakshadweep. Here you can see here, this is the power. So wherever there is a place, we have to keep the solar panel or solar parks. Now applications of solar power. Cumulative installation up to December 2019, the solar PV systems, lanterns and study lamps, then home lights. So solar power is used for home lights, street lights, solar pumps for pumping the water in the agriculture, or pumping the water from the wells for domestic purpose. Then solar PV plants. So the number we can see, lantern and study lamps, about 74,000 lamps have been powered by solar. Similarly, home lights, 17 lakhs 21,000 home lights have been lit by solar. Then street lights 6 lakhs 79,000. Solar pumps 2 lakh 46,000. And SPV plants standalone generated to 212 megawatt power. And other solar based domestic use or industrial use products are solar dryer, then solar cold storage, solar dryer for drying the textile or paper kind of thing, then solar cold storage, solar thermal based space heating system for design and development of highway efficiency solar water pumping system, supply of clean drinking water through Internet of Things based solar powered station at a large village in Haryana, okay, and solar PV battery charging stations for hybrid electric vehicles and electric vehicles. Then testing labs available for PV modules for time to time, okay. So crystal silicon PV cell, we have the Indian standard IS this number. Title of Indian standard is crystal silicon terrestrial PV module, design qualification and their type of approval. Then testing labs recognized by BIS is Physics Laboratory India Limited Pune, UL India Bangalore and TUV Bangalore. So there are the 3 companies looking after everything, and CPRI Bangalore also came into picture to test all the varieties of categories of PV module. Like thin film territorial, if you have thin film, you can go to these 2 companies. If you have silicon wafer and thin film, you go to this. And power inverter for use of solar power testing is facility, utility interconnected batteries, inverters, and the storage batteries. These are the standards. These are the qualification testing, and these are the test labs available. Okay. So all kind of infrastructure has been developed for successful commissioning and monitoring of the PV energy. Some of the grid-tied inverter manufacturers, ABB, AEG, Platinum, okay. There are Siemens, so many, Schneider, there are so many companies, okay, which will manufacture the inverters particularly for solar applications. Then some research areas, design and development of low cost, low power, high efficiency inverters. So there is a scope for research for you to design the inverters which can take low cost and low power and high efficiency. Then power performance analysis of PV power plants and different PV technologies, compare them. Then design and development of change controllers or charge controllers. Then changing switch. So changing from grid to battery or charge controller to the battery, charge controller to the load. So these are called change controllers. There should be a electronic version so that they will take nanoseconds or microseconds to get connected or get disconnected. Then power quality issues on power integration of PV plant or hybrid systems. Then harmonic analysis of solar inverters. Then design and development of data acquisition systems. And solar VFDs for water pumping application. Modeling and simulation of solar PV systems. Then smart integration of future grid connected system. PV performance, reliability and safety. Micro cracks on PV module. Then designing of low cost, low power tracking mechanism. So maximum power transfer tracking. So these are the areas, some of the areas, important areas for you to conduct the research if you want really to do it. Then we'll go to the wind energy maybe after the break. So shall we have a break, Krishna?
Yes, sir.
Yes, sir. We'll have a break about 5-10 minutes, whatever time you give. Then we'll start a wind and then go ahead. So that we'll have, enough gap between solar and wind.
Okay, sir. Shall we start at
At what time? 11?
40?
Okay, 11:40.
Okay, sir. Thank you. Dear participants, it's time for break. 10 minutes. The session will be resumed at 11:40.
వస్తుందేమో చూడు ఇయర్ ఫోన్స్ తో ఇంకో ట్రై చేయి అసలు ట్రై చేయి గమ్మున ఉండు ట్రై చేయి డాడ్
Hello, Krishna.
Yes, sir.
Shall we start?
Yes, sir.
Uchara andaru?
I'll remind them, sir.
Okay.
Sir, we will start, sir.
Okay. Back again. Wind energy generation scenario. We'll start about the wind energy now. India's cumulative wind power installation by different states total constituted to 37.7 gigawatt as of March 2020. So start from right, Kerala is 0.17%, the white patch, and then others 0.01, Tamil Nadu 25%, which is the highest. The yellow one is Gujarat 20%, then Maharashtra 13%, green one, light green, then brown 13%, Maharashtra, Karnataka same, Rajasthan 11%, Andhra Pradesh dark green 11%, then Madhya Pradesh the pink is 7%, and Telangana is 0.34%. So this is how the distribution of wind power across the country. You can see the potential here. Now this is our Indian map. So we have an Indian map. So we have the offshore sea is surrounded 3/4 parts, and we have different color codes. The wind power classification is made here on the right side. So dark blue dark blue indicates superb resource potential, and it is more than 800 watts per meter square at a height of 50 meters. At a hub height of 50 meters is calculated or estimated. So dark blue only at some parts here. Dark blue is only this area. Then if it is a red, outstanding 600 to 800 watts per square meter. So red is between Sri Lanka, between Sri Lanka and India, and Tamil Nadu coast, Kerala, covering Kerala and Tamil Nadu. Again in the Sri Lanka. Then violet is excellent between 500 to 600. This is the violet area. Okay. Then the pink one is good, 400 to 500. This border line is pink, both the sides. 3 yellow is fair, 300 to 400. So this is the yellow part. Okay. And the light pink is marginal, 200 to 300. The light pink is towards this Kerala and Maharashtra, Karnataka. Kerala and Karnataka. There is a pink one, and also here. So light pink is 200 to 300 watts per square meter. Then white one is very poor, 0 to 200. Where is white? Here. So this border is white. Okay. So that's how the wind power classification and potential is available, and we can explore them. But now we have explored only in the Gujarat, okay, this part, and also Tamil Nadu, this part. So there are 2 installations right now, but we need to explore the other installations across. Now, wind energy potential, expected growth in offshore turbine size globally. Okay, globally turbine size, blade size. So here in the bracket we have given nameplate capacity in megawatt, hub height in meters, HH is hub height in meters, rotor diameter in meters, which is classified as RD, specific power watts per square meter. So in the cruise, much earlier than year 2000, we have cruise ship 45 meters height, hub height, and then in 2000 the hub height was hub height was 64 meters, and now same hub height is risen to 80 meters between 2000 and 2005 year, and between 2005 and 2010, 5 years, the hub height 80 meters to 82 meters. And 2010 to 15, it has risen to 90 meters. Now, presently in 2017, 2015 to 2020, we are using 120 meters, 100 meters and 120 meters. In 2030, they are anticipating hub height of 125 meters as the highest. Till now, the highest is 120 meters. Okay, so because at 120 meters there is a lot of potential of wind energy transfer, so they have explored 125 meters also. Now we'll see the nameplate capacity of megawatt, which was 1.6 megawatt risen to 3 megawatts, then to 2.9, again risen, fallen, and then 4.1, and then it is 11 megawatts. Each turbine will generate 11 megawatt. And rotor diameter, you see 69 meters here, 90 meters, 94 meters, 119 meters, and 190 meters. Okay. And specific power watts per square meters, 435, 470, 420, 375, and 375. So even here also the watts per square meter area is same, 375. So this is the expected growth of offshore turbines. Okay, so in the sea. And wind power potential in India at 100 meters and 120 meters above the ground level. The first column gives the states, second column, middle column is at 100 meters height, then at last column is 120 meters height. You see the Andhra Pradesh state 44.23 gigawatt and 74.90 at 120 degrees and 44 at 100 meters. Then Gujarat 84.43 gigawatt at 100 meters, 142 at 120 meters. Karnataka 55, 124 respectively. Madhya Pradesh 10, 15. Maharashtra 45, 98. Rajasthan 18, 127. Tamil Nadu 33, 68. And total 7 windy states to contributing 292 gigawatt at 100 meters and 651 gigawatt at 120 meters. Other states all put together, remaining states 9.28 and 43.78 respectively. And all India total 302 and 695. This is the potential, wind power potential. So if you can explore 120, will generate double. If you explore at 100, we can generate 302. This 395, which these two figures we have given at earlier discussion also. And state-wise wind power installed. This is only potential. Now this is installed. So wind power installed are in Andhra Pradesh 4,092 megawatt installed are 4 gigawatt. Gujarat 7 gigawatt. Karnataka 4.7 gigawatt. Kerala 62 megawatt. Madhya Pradesh 2.5 gigawatt, Maharashtra 5 gigawatt, Rajasthan 4.2, Tamil Nadu 9.2, Telangana 128 megawatt, others 4.3 megawatts, total 37.5 megawatts. That is what we figured here, 37.7, okay, gigawatt. We can also see this potential here, locations of meteorological masks in the coastal area, then Gulf area of Kutch and Gulf area of Kambat. So we have explored the Kambat area in Gujarat, okay, offshore potential. And the year-wise electricity generation from wind energy sources from last 5 years, 5 financial years, 2014-15. Wind power is 33,000 million units. Then 2015-16 33,000, 16-17 46,000, 17-18 52,000, 18-19 62,000, up to 19-20, up to December 19, 2019, up to October 2019, 47,000. Okay, so this is the progress of the power generation year-wise. You can see the minimum tariffs which was discovered through tenders auctioned for wind power from various companies, various sections. So SECI 1 means Solar Energy Corporation of India 1, 2, 3 bidding, first bidding, second bidding, third bidding, fourth bidding, like that. So the capacity awarded was given in this column. Total 11,862 megawatt power or 11.8 gigawatt power has been tendered for private parties or the government parties to take up. The type is section 1 central. Then Tamil Nadu is a state, Gujarat state, Maharashtra state, remaining are central sector, and Gujarat again state sector. So the minimum tariff which was bidded was 3.46 rupees per kilowatt hour, and so on and so forth. The lowest is 2.43, 2 rupees 43 paisa is the lowest in Gujarat. Okay, so the highest bidding is 3.42, 3 rupees 42 paisa by Tamil Nadu. So this is the minimum charges of wind energy is possible. Then IREDA sector-wise breakup of cumulative loans sanctioned, that means investments made and disbursed, okay, in crores. So wind power Here sanction 650, disbursement is 500 crores. Then hydropower sanction is 650 crores, hydropower, mini hydro 50 crores, then 125 crores are biomass and cogeneration, then solar energy 600 crores, 20 crores waste to energy, then 1150 crores on lines of credit and short-term loans. So these are all the amount to 2,595 crores have been sanctioned and 3,974 has been disbursed. Okay, from total previous year and this year also. This is from 1/1/2022, 31/3/20, 3 months duration they have disbursed this amount. So that much investments have been made by IREDA. Offshore wind farms and hybrid wind solar system. So this is offshore in the sea, this is also in the sea, and this hybrid solar and land onshore wind energy conversion. Now these are the few of the institutions which have been sanctioned fellowships for MSc MTech students for pursuing junior research fellowship and senior research fellowship funded by MNRE, Ministry of New and Renewable Energy, under scheme NRI and NREF 2019-20 year. IIT Kharagpur, IIT Roorkee, Anna University Tamil Nadu, Pune University Pune Maharashtra, then Pondicherry University Pondicherry, Sri Mata Vaishnavi Devi University Katra at Jammu and Kashmir, Jalapur University Kolkata, and the Cochin University of Science and Technology Cochin, Indian Institute of Engineering, Science and Technology, West Bengal, then University of Lucknow, then National Physical Laboratory of CSIR, New Delhi, Central University of Jharkhand, Ranchi. So these are the institutions who have drawn some funding for research scholars, okay, as a fellowship. Now, what is wind power? Now we have seen the statistics, okay, potential and the wind energy. Now we'll see what is the wind power. So wind power as an alternative to fossil fuels is a abundant, renewable, widely spread, clean and produces no GHG emissions during operation. Wind is the world's rapid growing source of energy. Why wind energy? The majority of electricity is generated by burning coal rather than more eco-friendly methods like hydroelectric power. This use of coal causes untold environmental damage through carbon dioxide and other toxic emissions. Then the energy sector is by far the biggest source of these emissions, both in India and globally. And we are able to tackle the climate change. It is very clear that we need to move away from the burning limited fossil fuels reserves to more sustainable and renewable sources of energy. Now the wind design is very important in wind energy conversion system. A wind turbine is a complex electromechanical system consisting of many components and subsystems. Selection and design of wind turbine is done according to the demand, the location and the wind profile, with the prime motive of reduction in price and maximizing the energy capture. Then as a result of continuous research and development, now wind turbine of rating varying from several kilowatts to megawatts is available. The one of the important parameter of the wind turbine is its diameter. Then nowadays the emphasis is being given on turbine with long turbine blades, as longer blades have the capacity to sweep wind energy from larger areas and generate greater amount of output power. So more is the blade length, the more output power we can expect. Now wind turbine design, a small mathematics here, the relationships. Wind turbines are mainly of two types. One is horizontal type model, which is HAWT, horizontal axis wind turbine, and the vertical axis type model, vertical axis wind turbine, VAWT. Due to their greater efficiency, horizontal axis wind turbines are more preferred choice than the vertical axis. in most of the wind turbine industries. Modern wind turbine design explores or exploits advances in material, engineering aspect, electronics and aerodynamics. This equation is important. The mass flow rate of air through a cross-sectional area of A is dm by dt is A mu P, which is mass flow rate of air in kgs per second, where A is a cross-section of wind intercepted by the turbine in square meters. U is the wind velocity perpendicular to A area cross-section in meters per second. Rho is the density of air 1.2 kg per cubic meter as an estimated typical value. Wind power is calculated as a PW, which is equal to d omega by dw by dt, which is half the u square dm by dt, which is half the A rho and u cube in watts. That's how the power is calculated. The power is a function of A, u and rho. And again wind power turbine, wind turbine power is efficiency into this output power. Okay, so which is half efficiency A mu rho and u cube in watts. Okay, so turbine efficiency eta depends on turbine design, function of wind speed, a theoretical maximum value of just below 60%. Okay, that is the turbine efficiency. Now we will see the two varieties. Horizontal, this is the horizontal one, where the rotor diameter, this is the rotor length at one side, and the rotor blade shape, aerodynamically shaped. Then it is the hub is, this is a hub, front hub. The hub height is this height. Okay. Now the hub is connected to the gearbox, and the gearbox, the purpose of gearbox is to increase the speed. The wind velocity is very low, the blade velocity is very low. It has to convert to high speed to suit the generator speed. Okay, so this is a generator which generates the power. And then this is a tower. Okay, tower height is up to hub. Okay, is calculated 50 meters, 80 meters, 100 meters, 120 meters. In future 125 meters also. Then there is a vertical variety, very rarely used. The rotor diameter, this is the rotor. Okay, and a fixed pitch rotor blade and rotor height, and the generator is at the bottom, and the gearbox is also on the foot. You can see the typical power density, wind power density. This is the wind speed is given in knots. Okay, nautical miles per hour. Each 1 nautical mile per hour is roughly 0.5 miles per second. Okay, so 1 is equal to 0.5. Calm, this is calm area. Description is very calm. Power density is very low, watts per square meter, and 3 knots, 50 knots, 20 knots, and so on and so forth. Maximum 70 knots, which is called hurricane, which can generate 26,980, but it is damaging. Hurricane is not a normal situation, abnormal situation. Similarly, 40 is a gale, which gives the next 5,000. Then 25 is strong. Then we want from strong, fresh and moderate. Okay, so which can have 265, 625, 629, 1229 watts per meter square. This is the power density, and these are nautical miles per hour wind speed. And this is a description. You have to describe this situation. Then the internal parts, wind comes like this, and there is a hub. This is the hub. Okay, front to dome, and these are the blades, rotor blades. Then drive shaft, then the main gearbox, and then generator, and these are all called housing, and a rotating bearing here. So this is a rotating, because direction also should change. Okay, so the blade directions should change. So this base should rotate on the tower. Then the high speed shaft is a low speed shaft, and the block diagram is wind flow. We have turbine rotor, then gearbox, then generator, power converter, and load or grid. This aspect is mechanical aspect and this is the electrical aspect. You can see the various parts of wind turbine very fast. Rotor hub and blade. So we have seen rotor hub and also blade. And we have seen the gearbox. What is the speed here? Rotational speed of rotor blade is desirably it is 1000 to 3000 revolution per minute. So gearbox, gears and bearings are of two main components of gearbox. Okay, the rotor speed in wind turbine is ranging from 7 to 30 RPM. And gearbox ratio is typically 1:100 to 150. So your 30 RPM will be multiplied with 100. So you'll get 3000 RPM at the generator side. So gearbox is a speed amplifier. Okay. So the 6-pole generator rated RPM is 1000, 4-pole is 1500, 2-pole 3000. Okay. And in general 4 or 6-pole is used to have the lower speed. Okay, with a gearbox. The rotor speed of the wind turbine is not sufficient to produce electricity as most generators need the speed of 1000 to 3000 RPM. That is why there is a gearbox. So therefore gearbox increases the speed of the generator rotor to 1000 to 3000 to render the generator functional. The characteristic of wind turbine, power speed characteristic. You can see the mechanical power and speed. So the turbine speed and this is the turbine output power. Okay, mechanical power. And these are the curves. These are called turbine power characteristic. 10 meters per second, 9 meters, 8 meters, 6 and 5. Okay, these are maximum power at base wind speed of 9 meters per second. Okay, this is the lowest. So similarly here, wind turbine CP characteristic, pitch angle increases by every 2 degrees. So every 2 degrees there is an increment. Okay, so lambda versus CB. Then torque speed characteristic. We have torque on the left side, speed on RPM on the right side. So it is 500 meters per second is the blue one, lowest curve. Is red, 8 meters per second, and the green one is the highest, 10 meters per second. So these are typical torque versus speed characteristics of horizontal axis, two-bladed propeller type wind turbine. And now the generators, electrical part. Now in energy, the energy in the wind turbines, 2 or 3 propeller like blades. So mostly 3 blades are generating more wind velocity conversion into the high energy at the generator side. The rotor is connected to the main shaft and spins the generator to create electricity. These are all basics. Now generators have 2 types, asynchronous generators and synchronous generators. In asynchronous generator, we have squirrel cage induction generator, wound rotor induction generator, W-fed induction generator. And among the synchronous, wound rotor synchronous and permanent magnet synchronous generators. Then you can see the different types of wind energy conversion system. We have the blades, turbine blades, gearbox, squirrel cage induction generator, capacitor compensator, and then you have reactive power compensation, then grid connection point and the loads. And similarly the variable, this is a fixed speed. The variable speed wind turbine, you have wind turbine, gearbox, and then gearless also. You can have gearless if you have the permanent magnet synchronous generator. Okay, if you have gear, then wound rotor synchronous generator and squirrel cage induction generator. Okay, this is a generator and generates AC power. AC is converted to DC, and then DC is filtered here or alter the values. Then DC to AC, and then low frequency power factor. Low frequency power filters, and then the coupling transformers, and then utility grid. And the measured variables and reference variables are handled by the control systems to trigger these devices. Then squirrel cage, wound rotor, and W-fed induction generator. These are all induction generators in all the 3 cases. So we have blades, then gearbox, induction generator, soft starter, capacitor bank, transformer, grid. Similarly, blades, gear, variable resistance is a wound rotor. So control at the rotor side, okay, with the rotor resistance, okay, star connected. Then stop starters, capacitor bank, then the transformer and grid. Again blades, then doubly fed induction generator. The difference between three are, this is a doubly fed. So three windings, here three windings, there three windings. The stator windings are directly connected to the grid through a transformer, and the rotor windings are connected through the converter combination, DC link converters, AC to DC, DC to AC, again sent to the same grid. So there are two paths, okay. That is a doubly fed induction generator. Then wound rotor synchronous generator and permanent magnet synchronous generator. So there is a gear, then generator, synchronous generator, full scale frequency conversion, AC to DC, AC to DC, DC to AC, and then transformer and grid. Then a synchronous generator, we have DC to AC, and then directly connected, and this is the magnets, the wound magnet, okay, and this is the, you know, the stator. So this is the power generation. This needs excitation. So rotor field is excited through this AC power. AC is converted to DC. DC power is being excited. So once you excite, then the power generates once it is in rotation. And then if it is a PM generator, then you don't have this coil. This loop is absent because permanent magnets will generate the field in this. Okay, so we will have only stator. Stator generates AC power, AC to DC, filter, then DC to AC, appropriate voltage and frequency, then tap to the grid through transformer. And the DFIG and wind turbine system, you know, details of the diagram. We have wind turbine, the drivetrain or gearbox, then rotor, and rotor three phase is connected because it's a doubly fed, connected to the converter, converter to inverter, inverter to through transformer, it is to the grid. And similarly, the stator is directly connected to the grid in a doubly fed induction generator. Then if you see the active and reactive power flow in DFIG, with regard to subsynchronous speed. Now the stator is supplying power directly to the grid, and the rotor exciter needs excitation, okay, which is taken from this circuit from stator, from the source, grid source, then AC to DC, DC to AC, and then feed it to the exciter. Similarly, the power, this power, the stator is supplying power to the, you know, lines, grid lines, and the rotor power is taken from the source, red line. So stator power out, rotor power in, then it is called subsynchronous operation. And if both are supplying, both stator is supplying to the grid, rotor power is also supplying to the grid, then it is called super synchronous speed. This is with the case with a doubly fed induction generator. There are two modes of operation, subsynchronous and super synchronous. In super synchronous, both powers, rotor supplies and stator supplies power to the grid. And the control strategies for wind energy conversion, we have pitch control, the maximum power point tracking control, then rotor and grid side converter controls, rotor side converter and grid side converter. Okay, then the main functions of RSC and GSC are given here, and there are different control strategies like field oriented control, direct torque control, then voltage oriented control, and direct power control. And you can see the comparison of various generators used in the wind energy conversion system: induction generator, synchronous generator, permanent magnet synchronous generator, doubly fed induction generator. So induction generator pros and cons: full speed range, no brushes on the generator, complete control of reactive and active power, proven technology. Cons: full scale power converter is required, then no need for gear because it is a constant speed generator. Then synchronous generator, full speed range, possible to avoid gear because it's a variable speed. So complete control of reactive and reactive power, active power. Small converter for field is required in a wound field synchronous generator. Full scale power converter is also required. Then permanent magnet synchronous generator, full speed range, possible to avoid gear, complete control of reactive active power, brushless, low maintenance, no winding is required, no power converter for field is required. Full scale power converter is required, multipole generator, big and heavy, permanent magnets needed. Then doubly fed induction generator, limited speed range, -30 to +30% around synchronous speed, inexpensive small capacity PWM inverter, and complete control of reactive and active power. No need slip rings, need for gear. So these are the disadvantages. And then for future scope of research is variable speed, PMSG, DFIG may be used by eliminating gearbox. That is a research scope. To improve power quality in view of various grid faults can be addressed using various converter topologies and modulation techniques employed in grid side converter. To explore field oriented control, direct power control, voltage oriented control, direct power control for rotor side converter and grid side converter need to be explored. Use of multi-level inverters for higher levels of all varieties with various modulation techniques. Sinusoidal PWM, space vector modulation, space vector PWM, carrier based space vector PWM with IPD, POD, APOD techniques and so on and so forth need to be researched. Use of PI controller, PID controller, fuzzy logic controller, ANN controller, neurofuzzy combination, genetic algorithm controllers used in the control loop and explored. Digital implementation with DSC, FPGA, field programmable gate array, ASIC, application specific integrated circuit, etc. need to be implemented for fully digital operation. Integration of several wind energy conversion system into a warm wind farms. Several wind energy conversion systems connected into a one system is called wind farms. Then integration of solar PV with wind turbine based energy system is connected to a microgrid which is called hybrid system. Now challenges to grid connection. Challenges to grid integration of renewable energy in India. India has witnessed increasing capacity. Out of total installed capacity of 78 gigawatt, wind energy contributes to more than 35 gigawatt. Additions in renewable energy with installed capacity very close to 22 gigawatt for solar as on March 2019 against wind energy. Variability of resources. What are the challenges of grid connected renewable energy? Variability of resources, particularly the wind energy. The variability of resources. What does it mean? Power plants operations cannot control the wind and solar output because wind speeds and solar intensities vary dramatically, affecting power output. To balance the supply and demand on an instantaneous basis, there should be additional energy input as well as peripheral ancillary services such as voltage and frequency regulation. That is why we require to integrate both. Then unpredictability. We do not know when it will be available, when it will not be. So the availability of wind and solar are unpredictable to an extent. Electricity is produced when the wind is blowing and the presence of sunlight is crucial for PV systems to work. Then locational dependency. Quality wind and the solar resources that are most feasible for renewable energy generation are unfortunately based only in specific locations. So generation is co-located with the resources and the place where the power is ultimately used in often far from these locations. So the location dependence, unpredictability, variability of resources. Those are the three constants. Now hybrid renewable systems. Over last decade, solar has been the single largest contributor to green energy generation. It has zero emissions due to huge technological advancements in the field. Similarly, wind energy, a widely distributed renewable source, produces clean and economical power with zero emissions. And for climate change mitigation, the seamless harvesting of solar PV in combination with wind technology as a hybrid system is proving to be a key development. So the hybrid solar wind system will make economical sense in aiding growing economies with clean energy transformation to achieve development and climate goals. So the hybridization of the two technologies would help in minimizing the variability, optimally utilizing the infrastructure, including the land and transmission system. The existing wind farms have the scope to add solar PV capacity, and similarly, there may be wind potential in the vicinity of the existing solar PV plant. So either solar PV is moving to wind farms, existing wind farms, or wind farms will be created near the potential of solar plant. So in an appropriate capacity of battery storage may also be added to the project to reduce the variability of output power from wind solar hybrid plant, provide higher energy output for a given capacity at a delivery point by installing additional capacity of wind and solar power in the wind solar hybrid plant system, ensuring the availability of firm power, both powers, in combination for a particular period. Now we'll see the wind energy, hybrid wind solar PV grid integration. We'll see the picture. Offshore also we'll see. Offshore wind energy also see. One is hybrid, another is offshore. So this is a proposed single phase cascaded inverter fed from PV module and wind turbine. So you can see the PV module here. This is a PV cell, and then you have a capacitor, then you have a boost converter, and you have the cascaded inverter. This is a cascaded type multi-level inverter of 3 level. So it is a upper limb and this is a lower limb. Both are connected in series. So you can see this series combination. Okay. So the one output is getting out here. Sorry, which is connected to the load and also grid. Then we see other side wind energy, gearbox, and then the PMSG, then the converter AC to DC, and then filter, and then the boost converter, filter come boost converter, and then the lower limb of the cascaded inverter, and then it is connected to the load at the other end. So from solar and wind, both are connected to the same load or to the grid. So this is called hybrid system. Now this is a this above figure. Okay, you have the PV, and then this is one converter, this is an inverter, this is a converter, DC to DC boost, and this is an inverter, and these are all MPPT controller. Okay, and local controllers, generates PWM here, PWM. These are all local controller, master controller to sense the output of the grid voltage, grid current, grid frequency, and all that. Okay, then similar hybrid system. These are all the same discussion. What I made is given in sentences so that you can follow later also. Now power conversion of PMSG. This is the last slide, I think. When a wind energy conversion system with offshore. If it is offshore, how do you manage? Because the wind turbine is in the sea, in the mid of the sea. Okay, so there is a wind turbine, the gearbox, which is optional if you use a variable speed of PMSG or W-fed induction generator, which is variable speed. If it is a constant speed, we need this. If it is a variable speed, we can adjust the speed according to the wind turbine speed. So it is a PMSG, and then the AC to DC converter, machine side or rotor side converter, then DC chopper for boosting, then DC to AC inverter is a grid side inverter, and we have transformer. This is a transformer, step up transformer to suit the this is a grid actually. Okay, now from wind to this grid we have in the sea. Now after the sea, this is called offshore transformer, and this is a cable actually. Then offshore, this is a DC cable, HVDC cable. So it transfer the HVDC cable under the sea up to the onshore. And then we have offshore transformer at the other side, receiving end side. Then offshore converter we call AC to DC, and then DC cable, HVDC cable and then onshore converter we call DC to AC on the shore, and then we have connected that to the grid, onshore grid, high tension grid to transfer the power to the different locations. Okay, so this is the under the sea, and this is above the sea, on the land. So that's how we can. So HVDC plays major role here to transfer the power from sea to the land. This is called the offshore HVDC link of the wind energy conversion. Okay. Thank you very much. This is my email. You can post all your doubts at later stage. If you want to ask anything, you can ask me any clarification of this doubt. So this is a introduction come overview. Okay. Over to Krishna.
Thank you, sir. Thank you very much.
If there are any questions, we'll take. Otherwise, let them ask the doubts through my email.
Okay.
Okay.
Thank you, sir. Thank you for accepting our request in spite of your busy schedule. It was great session, sir, from you, and we had good technical stuff from this session, and it will be planted in our minds. Thank you, sir. So over to HOD, sir.
Thank you very much.
Thank you, sir.
Right.
HOD, sir.
Yes. Yes, sir, you can conclude, sir.
Yes, sir. You can talk, sir.
Sir, thank you very much, sir. Thus, in spite of your busy schedule, you have given us slot and you have taken as chief guest for this inaugural function also. Thank you very much, sir. Your session is very informative and having more information required for all the community of teaching faculty of EEE. Thank you very much, sir.
All the best. Thank you very much. All the best.
The next session will be started at 2 o'clock. Please join with us on time.
Uncle काय చెప్తారు?
Krishna sir.
Sir.
రికార్డింగ్ స్టాప్ చేసి తర్వాత ఎండ్ చేయండి.
Yes, sir. Yes, sir.